In this lesson, we will introduce some applications of determinants. First, we have the Cramer's rule. This is used to solve systems of linear equations with the use of determinants. So given a linear system with n equations and n unknowns, let A be the coefficient matrix of this system. So we write the system as AX equals B, where X is the column matrix for unknowns and B is the column matrix for the constant terms. If the determinant of A is not equal to 0, then the system has the unique solution x sub 1 equals the determinant of A sub 1 over the determinant of A. X sub 2 is equal to the determinant of A sub 2 over the determinant of A, and so on, up to x sub n, wherein it is equal to the determinant of A sub n over the determinant of A, where this A sub 1, A sub 2, and so on are the matrices obtained from A by replacing its corresponding column by the B, the constant terms. So if we have A sub 1, it is obtained by replacing the first column of A by your B. A sub 2 is obtained by replacing the second column of A by B, and so on. So to illustrate this, let us solve this example. We have, using the Cramer's rule, and given this linear system, let us find for x sub 1, x sub 2, and x sub 3. So first, we need to write the coefficient matrix of this system. So we name it as A. Coefficient matrix, we have negative 2, 3, negative 1, that's 1, 2, negative 1, negative 2, negative 1, 1. Okay. So from there, we will create our A sub 1, A sub 2, and A sub 3 by replacing the corresponding columns by B. So A sub 1 is equal to, so we will replace this by the constant terms. So our B is, we have 1, 4, negative 3. And then we'll copy the rest of the columns. We have negative 1, negative 1, 1. And for A sub 2, this time we will replace second column of A by the constant terms. So we have 1, 4, negative 3, 1, negative 1, 1. And lastly, for A sub 3, we will replace the third column by the B. So we have negative 2, 1, negative 2, 3, 2, negative 1, and then we have 1, 4, negative 3. Okay, and then next, what we're going to do is we will solve the determinant of each of these matrices. So let us move it here. Okay, so let us start with the determinant of A. So A is equal to, we have negative 1, 1, 2, negative 1, negative 2, negative 1, 1. Okay, so what we can do is we will apply the elementary row operations first so that we will have some zeros. So let's say, okay, so we have 1 here, so we will make these 2 zeros by adding third row by second row to yield 0 here, and then add also the third row to the first row to get a 0 here. So this row operation that we're going to apply will not change the determinant. So that's negative 2, negative 1, 1. Okay, and then we add these two columns so that we will yield a new row, these two rows to get the new row 2. So this is negative 1, 1, and then we have 0. And also we add the first row and the third row to get new row 1. So we have negative 4, 2, and then 0. Okay, so finally we have 2 zeros here, so we can do the cofactor expansion in this column, third column. So that will give us 1 times negative 1 raised to 3 plus 3. So that's third row, third column. And then we delete this third column and third row. So we have negative 4 to negative 1, 1. So this is equal to, this is positive because we have 6 here. And then we multiply this. So that's negative 4 minus negative 2. So that's negative 2. Okay, so that's our first determinant. Next, our determinant for a sub 1. Have 1, 3, negative 1, 4, 2, negative 1. Okay, so we apply again elementary row operations to get the rows here. So we do the same. We will add these rows, row 2 and row 3, and then next row 1 and row 3. So we add, that's 1, 1, and then 0. We add this, we have negative 2, 2, and then 0. Okay, we'll do the expansion here in this column. So we'll have 1, again, negative 1 raised to that times, we delete this row and column. So we have negative 2, 2, 1, 1. So that is, again, this is positive. So we have negative 2 minus 2, so that's negative 4. And for next, a sub 2 equals a sub 2, negative 2, 1, negative 1, 1, 4, negative 1, negative 2, negative 3, 1. Again, we can do the same. We will make this 0, the same steps. So we have negative 2, negative 3, 1. That's negative 1, 1, 0. We add this, we have negative 4, negative 2, and then 0. That is equal to 1 times negative 1. We expand in the same column, negative 4, negative 2, negative 1, 1. So again, this is positive. So we have here negative 4 minus 2. So that's negative 6. Negative 4 minus 2, yes. So that's negative 6. And let us solve now for the determinant of a sub 3. So that is, we have negative 2, 3, 1, 1, 2, 4, negative 2, negative 1, negative 3. Okay, this time, maybe we can make these two zeros, this negative 2 and negative 2 here. So we'll apply elementary row operations. That is, we will multiply this by 2, this row 2, and then we add to row 1, and then after that, we will add it to row 3. The same, we can multiply this by 2 since we have negative 2 and negative 2 here. So that's 1, 2, 4. So we multiply by 2, we add here, so that's 0. We multiply by 2, 4 plus 3, so that's 7. 8 plus 1, so that's 9. Then we multiply this also by 2, and then we add to third row. So that's 0. That's 3. And then this is 8 minus 3, so we have 5. Okay. And then we have two zeros here, so we will use, or we will do the expansion in this column. So that would be, we have 1, negative 1 raised to, this is in the second row and first column. And then we delete this column and this row. So we have 7, 9, 3, 5. This one will yield a negative sign, or negative 1. So we multiply this. So this is 35. So we'll have negative, and then 35 minus, that's 27. So that is equal to negative 8. So applying the formula, we will get x sub 1 is equal to the determinant of a sub 1 over the determinant of a. So this is equal to negative 2 over, that is, the determinant of a sub 1 is negative 4 over negative 2. So that means x sub 1 is equal to positive 2. Next, our x sub 2 is a determinant of a sub 2 over the determinant of a. So that's negative 6 over negative 2. So that's 3. And then finally, our x sub 3 is we have this. This is negative 8 divided by negative 2, so that is 4. So therefore, the solution to the system two, three, 4. So again, you can check your answer by substituting to this linear system. When you substitute 2, 3, 4 there, it should be 1, and so on. Next, the determinant can also be used in solving the area of a triangle in the xy plane. So the area of a triangle with vertices x sub 1, y sub 1, x sub 2, y sub 2, and x sub 3, y sub 3 is, we have positive negative 1/2 times the determinant of this matrix. So we have these vertices, and then we put 1 here, wherein the sign plus minus is chosen to give a positive area. So if you yield a negative determinant, then we will multiply it by negative, and then if it is already positive, then we will have that as the area. So for example, we have here, find the area of the triangle whose vertices are 1, 0, 2, 2, and 4, 3. So area is equal to 1/2 times the determinant of, we have here the vertices. We add 1 here, first vertex, 2, 2, then 1, and then we have 4, 3, 1. Next, we can do the expansion here in this row. So we will have 1 times negative 1, 1 plus 1. Or you can just simply use the sign pattern if it would be easier for you. So remember, this is plus, minus, plus, and then this minus, plus, minus, etc. And then we multiply, we delete this column and row. So we have 2, 1, 3, 1. Plus, we have 1 here. That's in the first row and third column. We delete this and this, so we will have 2, 2, 4, 3. Okay, and then we solve. We have this is positive, this is also positive. So this is 2. So that's 2 times 1 minus 3. So that's negative 1. And then this is also positive. So plus, we have this is 6 minus 8. So that's negative 2. Okay, so that is equal to, we have 1/2 times negative 3, which is equal to negative 3 over 2. But then again, since we don't have a negative area, so we will multiply this by negative. So therefore, our area, thus the area of the triangle is 3 over 2 square units. Now, if these 3 points lie on the same line, then the area is 0. So this determinant must be 0. So this can be generalized in the next theorem. So 3 points, x sub 1, y sub 1, x sub 2, y sub 2, and x sub 3, y sub 3 are collinear, meaning they lie on the same line if and only if the determinant of this matrix is equal to 0. So this is just the matrix we have in the previous application. Also, this test can be adapted for another use. We have, so given 2 points in xy plane, we can find an equation of the line passing through such points by solving the determinant of this matrix and then equate to 0. For example, we have Find an equation of the line passing through these 2 points, 2, 4, and negative 1, 3. So we have here the determinant of, we write xy and then 1. We write the points. We put 1 here and then negative 1, 3, 1. We equate that to 0. So we expand by cofactors in the first row so that we will have, so that's x. So that's positive because we have positive, negative, and then positive. So that's positive. We delete this, and this. So we have 4, 1, 3, 1. And then again, next is the negative. It corresponds to the negative position. So that's y times, we delete this row and this column. So we have 2, 1, negative 1, 1. And then this corresponds to positive sign. So we delete this and then this one. So we have 2, 4, negative 1, 3. Okay, that is equal to 0. Next, we find the determinants of these matrices. So that's x. We have 4 minus 3. So that's just 1. And then minus y times, this is 2 minus negative 1. So that is 3. So we'll just write down 3y. And then this is 2 times 3, so 6 minus negative 4, so that is 10. Okay, so that's plus 10 equals 0. Thus, the equation of the line is x minus 3y equals negative 10. Another application of determinant is for finding the volume of a tetrahedron. So given the following vertices of the tetrahedron, its volume is positive negative 1 over 6 times the determinant of this. These are the vertices of the tetrahedron. We just add 1 here, where again the sign plus minus is chosen to give a positive volume. For example, we have find the volume of the tetrahedron whose vertices are the following, which is shown below. So applying the given formula, we have here the volume equal to 1 over 6 times the determinant of, we'll just list down the vertices and we'll put 1 here. We have 4, 0, 0, and then 1. We have 3, 5, 2, 1, 2, 2, 5, 1. Okay, so let us move it in here. Now let us solve this determinant. So that is equal to 1 over 6 times, we'll do the expansion in the second row because we have the most zeros here. So we have 4, and this position here is negative because this is in the second row and first column. So that will yield a 3, exponent 3. So that's negative. So we'll write down negative there. And then we multiply by the matrix obtained, or the determinant of the matrix obtained, by deleting this row and this column. So we will have 4, 1, 1, 5, 2, 1, 2, 5, 1. Next, we have here 1, but this is in, we have negative, positive, negative, positive. So we have positive 1 there, and then times the remaining entries. So we delete this and this. So we have 0, 4, 1, 3, 5, 2, and then 2, 2, 5. Okay, and then we proceed. We will, maybe we can have, or we can apply the, since we don't have 0 here, we can apply some row, elementary row operations. We'll have negative 4 times, I think it would be easier if we will make this 2 entries here 0. So what we do is we can multiply this by negative and then we add to this row and then also to this row. So that's times negative 1. So that's 1. We have 1 and then this becomes 0. Again, we multiply by negative 1 here and then we add to this row. So that's negative 2, 4, and then 0. Plus, we can just remove 1 there. So we can also make some more 0 maybe here. So we can multiply this by negative 4 and then we add to this. We multiply this by negative 4 and then we add to the second column. So we will just write down the first column. So times negative 4 and then add, so that's 0. Times negative 4, so that's negative 8 plus 5, so that's negative 3. We multiply by negative 4, so that's negative 20 plus 2, so that's negative 18. And then we have 1, 2, 5. Okay, and then we proceed with the cofactor expansion. We have here, that's negative 4 times, we'll do the expansion here, cofactor expansion. So we will just have 1, but this is positive, negative, positive. So we will just have 1 times the determinant of, delete this. So we have 1, 1, negative 2, 4. And then plus, we'll do the expansion in this row. So that's 1, positive, negative, positive. So that's positive times, we have the remaining matrix, 2, negative 18. Okay, and then finally, we will solve for the determinants of the 2 by 2 matrices. 1 over 6. We have negative 4 times, this is 4 minus negative 2, so that is 6. And then plus, this is 3 times 18. So that's negative 54, and then minus negative 6, so that would give us, again, that's negative 54, so we'll have negative 48. Okay, and then this is equal to 1 over 6 times, we have, this is negative 24 plus negative 48, so that's negative 72, right? So it's negative 72, and then divide it by 6, so we will have negative 12. So again, we don't have a negative volume, so we will just multiply that by negative, so that will become positive. Therefore, we have the volume is 12 cubic units. So from here, we have now the test for coplanar points in space. So coplanar points are points in three-dimensional space that lie in the same plane. So for points, we have this, are coplanar if and only if the determinant of this matrix is equal to 0. Next, we have the 3-point form of the equation of a plane. So this is an adaptation of this test here. So an equation of the plane passing through the distinct points x sub 1, y sub 1, x sub 1, and so on is given by the determinant of this. We have x, y, z, the unknown, and then we have the following points here. So the point 1, 2, and 3, and then we add 1, so that is equal to 0. So an example for this, we have find an equation of the plane passing through the 3 points, 0, 1, 0, negative 1, 3, 2, and negative 2, 0, 1. So we apply the formula. We have the determinant of the matrix, x, y, z, we add 1. Then the points, we have 0, 1, 0, we put 1 here. -1, 3, 2, 1, and -2, 0, 1, 1. This is equal to 0. So first, we can make this 0 by multiplying this by -1, and then we add it in this column. So we'll just change this column first. X 0, -1, -2. So we multiply by negative and we add it here. So that's y minus 1. This becomes 0. We multiply by -1 plus 3. So that's 2. We multiply by -1 plus 0. So that's -1. And we have z 0 to 1. We have 1, 1, 1. So that is equal to 0. Next, we'll do the cofactor expansion in this column. A row rather, row. So row 2, so we have here 1. This position rather, this position is we have positive, negative, so that's positive. Okay, so we will have positive 1, and then we write down, when we delete this column and row, we write down the remaining matrix. So that's x, y minus 1, z, -1, 2, 2, -2, -1, 1. Now again, take note, we don't have these numbers there because we just use the sign pattern. So this corresponds to the negative sign here, this position. So next, we will apply the cofactor expansion in this row so that we get x times, this is positive here, so we'll have a positive cofactor. So we'll delete this row and then this column, so that is 2 to -1, 1. Next, this corresponds to the negative, this position, negative, we have y minus 1 times, we delete this row and column, so -1 to -2, 1. Then plus, we have z, this is positive, so we remove this. We have -1 to -2, -1. It's equal to 0. Next, we'll solve for the determinants of these 2 by 2 matrices. So we have 2 minus -2, that's 4. So we have 4x. And then minus y minus 1. We have here, this is -1 minus -4, so that's 3, positive 3. And then plus, we have positive 1 minus -4. Am I right? This is positive 1 minus -4, so that is 5. So we'll have 5z equals 0. And then we multiply this 3 here, so therefore we will have 4x minus 3y plus 5z equals, this one is -3 times negative, so that's positive 3 with transpose on the other side, so that's -3. So therefore we have now the equation of the plane passing through the given points. Okay, so that's the end of our discussion for chapter 2.